Hey everybody, today we're going to talk about the history of the atom. So we're going to go through quite a few people and how we came up with that the atom is made up of our protons, neutrons, and electrons. So we're going to start way back in 350 BC. This is before Christ, so really, really long time ago. Start with Aristotle. Aristotle was a philosopher. So the key thing to think about is that he did no scientific research or anything to come up with his theory. He said that all matter is a combination of fire, air, earth, or water. So basically, nature is all made up of matter. Okay. Then we also have Democritus about the same time period, about 400 BC, also in Greece there. And he said that matter was made up of indivisible substances. And he was actually the first person to coin these indivisible substances as atomos. And what's interesting is even though the structure or idea of an atom has changed over time, that we still use that term atomos. We then go an awfully long time with just kind of an idea of matter is made up of things. We come to Antoine Lavoisier, and he really came up with this law of conservation of mass or law of conservation of matter, whereas matter can't be created or destroyed. So all the matter in the world that we have right now is the same stuff as it was in 1784. And then we also have this guy, Joseph Proust. And you'll notice that this is just a few years after the previous guy. He came up with this law of definite proportions. Okay, this is where elements and compounds come together in fixed ratios. So if you take a look at CO2, carbon dioxide, it is always a fixed ratio of 1 carbon to 2 oxygen. This law of definite proportions is still true today because that's how we write formulas. Those subscripts are never decimals. They are always small whole numbers. We now come to John Dalton. Okay, John Dalton is the one that said 2 elements can come together and form 1 compound. So that is how we come up with CO2. Carbon and oxygen come together and they form that CO2. And the way that they do form is those small whole numbers. Some of these guys you may be familiar with in other classes that you may have talked about. So with also John Dalton in 1805, so truly if you think about that, 1805, it was really only 220 years ago. In the grand scheme of things, 220 years ago really was not that long ago. John Dalton is the first guy that came up with an atomic theory. His was kind of a solid sphere, so he thought the atom was completely solid. Okay, he said elements are made up of indivisible particles. These indivisible particles he called atoms still, just like the Greeks. Each element was composed of the same kind of atoms. So if I take a look at all the potassium atoms in the world, they were all the same. Different elements were composed of different things. So if I looked at potassium and hydrogen, all the hydrogens would be the same, all the potassium would be the same, but if we compare the two, they would be different. Then compounds are composed of atoms in specific ratios. So that's when I talked about carbon dioxide. It is always a small whole number ratio. As well as atoms are not created or destroyed in a reaction. They are just rearranged. Now, as we keep going further and further into what we know now about the structure of the atom, some of these things that Dalton had said are still true today. Some of them are not true. It's just with scientific theories, they have to start somewhere. So here are some problems or issues that weren't known about yet, and we'll even hit upon them. Matter is composed of indivisible particles. Well, we know now today that inside that atom we have electrons, protons, and neutrons. So there is something smaller than the atom. All atoms of a particular element are identical? Not entirely. Okay, these are what we refer to as isotopes, and we're going to talk about that more in a little bit. Different elements have different atoms. That's still true. Atoms combine in whole number ratios. That's still true. And atoms cannot be created or destroyed, well, except with nuclear explosions. Okay, nuclear explosions destroy matter. We can change from one element to a completely different element. We then move on to J.J. Thomson, just a few years after Dalton. He said atoms aren't the smallest particle. There is something smaller than an atom. He conducted what we refer to as the cathode ray tube, or the CRT. He discovered that particles have a negative charge. So that negative charge is my electron. So the first smallest particle that was discovered was the electron. This is what we refer to as the plum pudding model. However, most of you guys have no idea what a plum pudding is. And so I usually refer to it as the chocolate chip model. So if you look at that picture there, it kind of looks like a chocolate chip. The cookie dough part is my atom, okay? The cookie dough, it's still solid, and then my chocolate chips are my electrons, and they are spread all throughout that atom. And so this is what a cathode ray tube looks like. And the reason why he figured out how they were negatively charged is he put a magnet next to it. And we know like charges repel and opposites attract. Okay, so the picture on the left there, you'll see that it's bending towards the light. That means that that beam is negative because the magnet was being shown that positive side. If he flipped the magnet over to the negative side, it would repel away, proving that that beam of light had a negative charge in it, which we refer to as electrons. So Thomson's interpretation of the model of the atom, it takes the place of Dalton's first statement. The atom is breakable, meaning there is something smaller in the atom, which is our electrons. So now these atoms, these electrons are suspended in a positively charged electric field because we still believed that the atom was neutral. So if he discovered a negative charge, there had to be some positive charge to balance it out. So predictions of the plum pudding model. The mass of the atom is due to the mass of the electrons. So if an atom weighed, say, 2 grams, that was because of the electrons in that atom. And there must be a ton of empty space in the atom. Since the electrons are negative, we assume you must keep them apart because they like to repel each other. So you can't get them very, very close to each other. So there's another picture of my plum pudding model. Okay, you'll see that the pink part is all positively charged, and then my electrons, they're all throughout on the surface. Inside, those are my negatively charged atoms. We then move on to Robert Millikan. He was the one that discovered actually the mass of the electron. He ran an experiment referred to as the oil drop experiment. And that's because all he did was he dropped little drops of oil, okay? He verified that the electron was negative, okay? And you'll notice there's some coulombs there. That is actually the charge. You really don't need to memorize that. But with Millikan, he was just confirming and verifying that the electron was negatively charged. And so with Millikan, there is really no new model, just verification. Now we move to Ernst Rutherford. He conducted the gold foil experiment. Why the gold foil? Because he used gold foil to work on the structure of the atom. He proved that one, that there was a nucleus, that nucleus was dense, positively charged, and in the center of the atom. So how did he do this? Okay. What he did was he stuck a piece of gold foil in the center, and then he took some alpha particles, a radioactive sample, and shot it at the gold foil. Because he thought the atom had tons of empty space, he thought most of the atoms or most of those alpha rays were going to go straight through and hit the barrier. Okay. What actually happened was most of the atoms did go through, which meant that the atom was mostly empty space. However, there were a few that were deflected, okay, and some shot straight back and did not go through, which meant it hit a very dense particle in the center, and the ones that were deflected, that meant that it was hitting some, or it was getting near something that was positive. Because those alpha particles were negatively charged, that means, or the positively charged, sorry, like charges repel. So when it got close to something positive, it actually repelled it. So his conclusions were actually crucial. Number one, atom was mostly empty space. That atom contained a dense particle that was very, very small in volume, but very large in mass. So most of the atom's mass actually comes from the nucleus. And this dense particle was positively charged, which is what we know as our protons. Okay. So in conclusion, Rutherford, he came up with the nucleus. That nucleus was the entire mass of the atom. Because my electrons were so small that even if we were to add them, it would be a very, very small fraction. So we sort of ignore them in terms of the mass of the atom. And that nucleus was positively charged. And so that's why we call those positively charged particles protons. And then those electrons are dispersed somewhere in that empty space surrounding the nucleus. We then come to Niels Bohr. This is kind of like our planetary model. He dealt with, where are these electrons? Are they just floating around, or are they in a particular spot? He said that electrons were like our planets, where they travel in the rings around the nucleus. So our planet, the sun, is our nucleus, or in our solar system, the sun is the nucleus, and all the planets are in a very specific path around the nucleus. That's what he said the electrons do. However, he also said that those electrons can move between energy levels. So if we have the first energy level, electrons can skip from one to the second. Okay, so if you look at this picture, you'll see that these electrons are traveling in very specific paths, but they can move further out and join another path. There were many, many people, and there's still many people dealing with where these electrons, because they're so small and the way that they behave, it's really hard. One guy is also Schrodinger. He determined the path of the electrons. Okay, he was a mathematician, so he dealt with the mathematical process of how to do this. What he also determined is that the electron, they're never in really one place. It's more of a probability that they will be in one particular place at this particular moment. Then we go to James Chadwick. James Chadwick, he actually confirmed the existence of my neutrons, okay? Because he said, okay, well, we have this nucleus with a whole bunch of positively charged. Well, positive charges, they like to repel each other. So there has to be something else in there that kind of helps them hold together. And this is my neutrons in the nucleus.